Good morning. We're talking about poisson distribution. Last class we just looked into the properties, the curve, and other things, and how well the approximation works when we actually look into binomial distribution when p equals 0. So today we'll derive the PDF. Okay. So the first question under this particular topic, poisson distribution, is I have a case derive the Pmf of poisson distribution, or the question could also be put as obtain the limiting form of binomial Pmf. Obtain the limiting form of binomial Pmf. Now the condition is important. So what are the conditions? So we have p of x is equal to x as ncx, p to the power of x, q to the power of n minus x, with x equals 0, 1 to n and 0 less than p less than 1 is the Pmf of binomial. And when n tends to infinity and p tends to 0, then with lambda equals np, binomial tends to poisson with Pmf e power minus lambda, lambda power x by x factorial, and x taking the value 0, 1 to infinity, lambda greater than 0. So now in this theorem, we will apply these limits to this Pmf, we'll evaluate the limits, and we'll show that we'll get this particular form. Okay. Fine. So if they say state the conditions under which binomial tends to poisson, we have to write this. So binomial tends to poisson when n is large and p is small, with lambda equals n. So now we'll take the limit of that. So consider limit n tends to infinity, p tends to 0, ncx, p to the power of x, q to the power of n minus x. So we have q equals 1 minus p. So we have lambda taken as np. So this implies we can write p as lambda divided by n, because working with two limits simultaneously becomes difficult. So somewhat if I reduce everything into either in the form of n or in the form of p, then working becomes very easy. So we'll change this terms involving p into lambda by n, so that the limit could be just simplified. So limit n tends to infinity. So I'll just write everything in terms of lambda, e to the power of x. So lambda by n to the power of x, 1 minus lambda by n to the power of n minus x. Now the terms doesn't involve any p, so I can remove that p tends to 0 and just step. Now just simplify and put limit n tends to infinity. So I have ncx, so I have to expand that n factorial, n minus x factorial, x factorial. Then I'll have lambda power x by n power x, then 1 minus lambda by n to the power of n divided by 1 minus lambda power n to the power of x, because it is n minus x. So now a power m minus n is equal to a power m by a power n. So we'll just split the powers like that. Now expand n factorial. Now since our x is an integer starting from 0 taking up to n, if I expand n factorial, after some point of time I'll reach value x before reaching 1. So you have n factorial is equal to n into n minus 1, n minus and so on up to 1. So somewhere here you will observe definitely n minus x, and you can have n minus x factorial. So I'll expand this n factorial as n into n minus 1 up to n minus x. Therefore, that x, get cancels. And then we have n power x. We have to take care of that. And here when I put n tends to infinity, I get lambda by infinity, which is 0. And 1 minus 0 to the power of x is 1 power x, which is equal to 1. And this x factorial is independent of the limit because it doesn't carry any term n. So that can be taken outside. And again, lambda power x doesn't carry any term n. Therefore, that can be taken outside. So what we do now, we take x factorial lambda power x outside the limit because they are independent of the limit. And now we expand n factorial. So n factorial becomes n into n minus 1 into n minus 2, etc. up to n minus x factorial divided by n minus x factorial. And then we have this term. So I'll write it out, lambda by n to the power of n. Now we'll leave this because limit n tends to infinity, 1 minus lambda power n whole to the power of x goes to 1 when I put n as infinity. Okay, and then we have an n power x. So x factorial get cancelled. Now if you count how many such n's are there in the numerator, now n minus x, its previous term is n minus x minus 1. N minus x minus 1. Let me write it here. So we have lambda power x, x factorial, limit n tends to infinity, n into n minus 1, etc. n minus of x minus 1 into n minus x factorial. So if you look in the previous term, that helps in counting the terms easily. And then you have 1 minus lambda power n whole to the power of n. So please be careful. Only the denominator term has been vanished. So this step I have written here, and you write this within the bracket in the next step. So that the term is also taken here. Now, we can cancel this. Now count how many such n's are there. So I have 1, n minus 1, 1, then n minus 2, so 2n, 3n, and so on up to x minus 1n, and then you have n here. Now what we do is, we take this n outside in every term, so I'll get n into n, n into n, so many times, that is equal to x times, so that I get n power x, and this n power x get cancels. Now always, working with the limit, as far as possible, try to see whether terms are, common and cancel out the common terms. So I'll have n, then n into 1 by 1, 1 minus 1 by 1. So in n minus 1, I'm taking n outside. So if I do that, I'll get 1 minus 1 by n. So again, the next term, it will be n minus 2. If I take n outside, I get 1 minus 2 by n. Then I have n minus 3, n minus 4, and so on. So in every term, I take that n outside. So in the last term, I'll have n into 1 minus x minus 1 by n. So we have got several n's there. And then 1 minus lambda by n to the power of n. Then I have n to the power of x. So we have x n's in the numerator and n power x in the denominator. So it gets cancels. And when you apply the limit now, when you put n equals infinity, see in all these terms, so we have n power x getting cancelled. And when I put n equals infinity, each of these terms becomes 1 minus 0, because 1 by infinity, 2 by infinity, and x is also finite, x minus 1 by infinity is also 0. So I end up getting 1, 1, 1 after substituting the limit. So the only term we have is this. And this is a known form of limit. Limit x tends to, n tends to, x tends to infinity, 1 minus, say, a by x to the power of x is equal to e power minus a, or x ಗೆ ಲಿಮಿಟ್ ಹಾಕಿದಾಗ. So this is a known limit. They might have learned that in the form of x, I guess, in the first PUC. So if I apply that, I get e power minus lambda. So your NCx p to the power of x q to the power of n minus x under the limit n tends to infinity and t tends to 0 has become lambda power x e power minus lambda by x factorial, so which is the Pmf of poisson. ಇದೊಂದು ಕಾಮನ್ ಆಗಿ ಕೇಳುವಂತ ಕ್ವೆಶ್ಚನ್ ಯಾವಾಗಲೂ. Derive the PDF of poisson or show that binomial distribution tends to poisson when n tends to infinity, p tends to 0. So the important steps are: first step, you will converting p to lambda by n everywhere in the PMF, and then you will take out the limit p tends to 0 because no more p terms available in the under the limit there. And then next step, you will split the power. So you have 1 minus p to the power of n minus x. You will write that as 1 minus lambda by n to the power of n divided by 1 minus lambda by n to the power of x. And when you put n tends to infinity for this, it becomes 1. Next step, you will expand ncx up to n minus x factorial. You will cancel n minus x factorial. In the remaining terms, in every term you will take n. You will get x times n, so that n power x also get cancelled. Then you are just left with this term. It becomes e power minus lambda. Lambda power x and x factorial are already out. Okay, so we got the functional form of the PMF. Now, now we have to verify whether it is PMF or not. Class join ಆಗಕ್ಕೆ ಏನಾದ್ರು ತೊಂದರೆ ಆಗ್ತಿದೆಯಾ? ಆಯ್ತಾಯ್ತು. Next, we'll have to show that it is a PMF. So in every distribution, so we will show the function PMF is actually a mass function. So define Poisson PMF or Poisson distribution and verify or show that it is a PMF. Show that it is a PMF. So that is the most commonly asked question, not only for Poisson, even for other cases like binomial, even for the next case, which is geometric. In all the cases, they'll ask this question. So define a particular distribution and show that it is a PMF. We have PMF of x equals x equals e power minus lambda power x by x factorial, with x taking value 0, 1 to infinity and lambda greater than 0. Now to verify it is PMF, to verify p of x equals x is a PMF, we have to show that summation x equals 0, 1 to infinity e power minus lambda, lambda power x by x factorial is equal to 1. So this is the condition. And also we have to show that p of x equals x is greater than or equal to 0 for all x. So, but that is easily observed. So in almost all the PMF cases, the function is defined such that whatever may be you substitute as x, of course within the range of x, you will always observe positive value. You can easily prove this. E power minus lambda is always positive. Lambda power x is always positive because your x is 0, 1 and so on, and lambda greater than 0. So lambda is a positive number, x is a positive number, therefore lambda power x is always positive, and x factorial is also positive. So you are dealing with three positive terms, so always their product and quotient is positive. So this is easily observed. That is nothing to write or state that. Now we have to check whether when I substitute the values of x from 0 up to infinity and expand this sum, do I get the term equal to 1? That is the question. So we'll check that. So e power minus lambda doesn't have anything to do with x. So I can easily take that outside the summation sign. So I can write this as x equals 0, 1 to infinity lambda power x by x factorial. So now what we do is we put x equals 0, 1 and so on, and we expand the sum. So when I put x equals 0, I get lambda power 0 by 0 factorial, lambda power 1 by 1 factorial, lambda 2 by 2 factorial, and so on. Up to infinity. Lambda power infinity by infinity factorial. So we usually don't write that. We just say the term carries up to infinite terms. Now if you look into what you have received after expanding the sum, that is almost a familiar series, which is 1 plus lambda by 1 factorial plus lambda square by 2 factorial and so on, etc. And if you look into the expansion of e power minus x or e power x is also 1 plus x by 1 factorial, x square by 2 factorial, and so on. So this is the Taylor expansion of the Taylor series for e power x. And we have the same case, but in place of x, we have lambda. So this becomes e power lambda. Now you have e power minus lambda into e power lambda, which becomes e power minus lambda plus lambda, which is equal to e power 0, and e power 0 is equal to 1. So very simple proof compared to the binomial proof. So we'll just put x equals 0, 1 to infinity. Whatever you observe, you take that as e power lambda, you will get equal to 1. So even if you forget this particular formula or anything else, so just we have e power minus lambda. If I want to observe that as equal to 1, whatever I have, that should come to e power lambda, only then it becomes 1. So expand it, take that as e power lambda, you will get your answer, required answer. So we have proved that the function given as e power minus lambda, lambda power x by x factorial is actually a PMF. Now we'll observe the next properties like mean, our variance, and also we'll look into the higher moments. And what I do is I'll just derive the MGF and we'll look into the moments based on the MGF, because in binomial we observe that whenever we have x factorial or NCX form, it is difficult to obtain the moments. Okay, you cannot directly obtain EX, EX square, EX cube. You can obtain EX square by computing E of x into x minus 1. So we have what called as factorial moments. From the factorial moments, we can obtain this, and from this, we can obtain the central moments. So instead of taking that long, lead, what we do is we'll just consider the MGF. From the MGF, it is easy to obtain EX square, EX cube. So we'll just stick to that particular method. On the other hand, you can try out with the factorial moments for Poisson and see what is the R factorial moment and so on. So you can take that as a homework. So I have to give you an assignment. Let me give, I'll have first question, deriving beta 1 and beta 2 of binomial distribution, and then R factorial moment of Poisson, and then beta 2 of geometric distribution. Geometric will be starting in the next week. So these are the 3 questions. Each of you have to write it in a sheet, A4 sheet, or any other sheet is fine, but don't send me any attachments now. So you will get the hard copy. So I need hard copy, and another 10-15 days you will get the message from us that the college will start only for those who have taken the vaccination, I guess. So please be ready with your practical records as well as the assignments. All the assignments, test papers, ಕೇಳಬಹುದು ಬೇರೆಯವರು ಟೆಸ್ಟ್ ಕೊಟ್ಟಿದ್ರೆ ನೋಡೋಣ. So where was I? We have to obtain mean and variance of binomial. Mean and variance of poisson. So mean is very easy to obtain, but when I look into the variance E of x square becomes somewhat difficult. So mean equals E of x, and by definition E of x is equal to summation of x into px under all possible values of x. So here the values of x are x equals 0 to infinity. I'll have x into e power minus lambda, lambda power x by x factorial. So I can cancel out 1x and I will take this e power minus lambda outside. So I'll have summation x equals 0, 1 to infinity, x into lambda power x by x factorial. Now you can simply substitute x equals 0. So even in that case, you will start sum from 0 and then 1.
ಸರ್ ಸರ್ ನಾವು ಕ್ಲಾಸಲ್ಲಿ ಇರಲಿಲ್ಲ ಸರ್, ಇಷ್ಟೊತ್ತು ಡಿಸ್ಕನೆಕ್ಟ್ ಆಗಿತ್ತು.
ಅದಕ್ಕೆ ಮಾಡ್ತಾ ಇದ್ರಾ? ನಿಮ್ ಕಡೆ ನೆಟ್ವರ್ಕ್ ಪ್ರಾಬ್ಲಮ್ ಇದ್ರೆ ನನಗೆ ಕಾಲ್ ಮಾಡಿ ಯಾಕೆ ಡಿಸ್ಟರ್ಬ್ ಮಾಡ್ಬೇಕು? ಟ್ರೈ ಮಾಡ್ಬೇಕಲ್ವಾ? ನಾ ಕಾಲ್ ರಿಸೀವ್ ಮಾಡಿದ್ರೆ ಇಡೀ ಕ್ಲಾಸೇ ಕಟ್ ಆಗುತ್ತೆ. ಅಷ್ಟು ಸೆನ್ಸ್ ಕೂಡ ಇಲ್ಲ.
ಇಲ್ಲ ಸರ್, ಎಲ್ರು ಸುಮಾರು ಜನಕ್ಕೆ ಎಲ್ರಿಗೂ ಆಗಿತ್ತು.
ಅದೇ ಅದಕ್ಕೆ ರೆಕಾರ್ಡಿಂಗ್ ಮಾಡುತ್ತಾನೆ. ಶೇರ್ ದ ರೆಕಾರ್ಡಿಂಗ್, ಡೋಂಟ್ ವರಿ. 2 ಥಿಯರಮ್ ಏನೋ ಡಿರೈವ್ ಮಾಡಿದೀವಿ ಅಷ್ಟೇ, ಅದು ಈಸಿ ಇದೆ, ಮಾಡ್ಕೋಬಹುದು. ವಿಡಿಯೋ ನೋಡ್ಕೊಳ್ಳಿ, ಡೌಟ್ ಇದ್ರೆ ನೆಕ್ಸ್ಟ್ ಕ್ಲಾಸ್ ಕ್ಲಿಯರ್ ಮಾಡ್ಕೊಳ್ಳಿ. ಇಲ್ಲಿಂದ ಶುರು ಮಾಡ್ಕೊಳ್ಳಿ. ಮೀನ್ ಅಂಡ್ ವೇರಿಯನ್ಸ್ ಆಫ್ Poisson distribution. So we have definition of mean, summation of x into px, and px of Poisson is e power minus lambda, lambda power x by x factorial. So when I put x equals 0, 1 and so on, I observe that I get 0 lambda power 0 by 0 factorial plus 1 lambda power 1 by 1 factorial, lambda power 2 by 2 factorial, and so on. And that is the lambda. Okay, so I'll have 2 into lambda square, 3 into lambda cube. Now this is called as a geometric series. So we have the result on geometric distribution, but that is a complicated step. So let me not do that process. So what I do is first I'll cancel out this x. So the problem is with respect to x. So I'll try to cancel this x, and then if I look into the expansion, that becomes very easy. So before expanding, let us cancel x. And these are the 3 assignment questions. Just copy it down. When the college starts, you have to get them. I need the hard copy. So another 10-15 days, you will receive the notification that the college will start. So pending work library, ಸ್ವಲ್ಪ complete ಮಾಡ್ಕೊಳ್ಳಿ. So consider this, even without cancelling, you can do that. For that, you need the knowledge of geometric distribution, so which is not yet done. So let me not use that result. So I'll simplify this and then I'll expand. Now when I do the expansion, I get x is equal to 0. So lambda power 0. When the x get cancelled, the sum automatically starts from 1. So I have given you the enough reason dealing with the binomial distribution. So when you put x equals 0 and when you put x is equal to 1, both lead to 0. So that's why we say the sum starts from x is equal to 1. So we can write it. This is the same as sigma x is equal to 1 to infinity lambda power x by x minus 1 factorial. So when you put x is equal to 1, you get lambda by 0 factorial plus lambda square by 1 factorial, lambda cube by 2 factorial, etc., which is the form of exponential expansion. But our exponential expansion is of the form e power x is equal to 1 plus x by 1 factorial, x square by 2 factorial, and so on. But here I have lambda starting from lambda. So if I take out that lambda common outside, I'll get 1 plus lambda by 1 factorial, lambda square by 2 factorial, and so on. So which becomes e power lambda. So I have lambda e power minus lambda, and this sum has become e power lambda because of this. So you get lambda into e power minus lambda plus lambda, lambda e power 0, just lambda into 1. This is the value of e of x. Therefore, the mean of poisson distribution is e of x equal to lambda. Now we need e of x square for variance, but we cannot compute e of x square because of the x factorial. And I have told you, whenever you are dealing with MCX or the term involving x factorial in the PMF, then computation of ex square, ax cube becomes difficult. So you have to use the factorial technique. So we can compute e of x into x minus 1, which is basically e of x square minus e of x. So from that you can obtain e of x square as e of x into x minus 1 plus e of x. So we can obtain this easily because we have x factorial. You can expand the x factorial of x minus 2 and these get cancelled and you can easily obtain the value. So let us see how we obtain this now. Consider e of x into x minus. So by the definition, that will be summation over x into x minus 1 into e of x. So which is for poisson x equals 0, 1 to infinity, x into x minus 1 into e power minus lambda, lambda square by lambda power x by x factorial. Now take this e power minus lambda outside because it is independent of the term 0. Expand your x factorial as x into x minus 1 into x minus 2 factorial. You have summation x equals 0 to infinity, x into x minus 1. So they get cancelled. So your sum now automatically starts from 2. Lambda power x by x minus 2 factorial. So we have e power minus lambda. Now when you put x equals 2, you'll get lambda square by 0 factorial, lambda cube by 1 factorial lambda power 4 by 2 factorial and so on. And if you want to apply this definition, I have lambda square in excess in every term. So take out that lambda square outside. We'll have now 1 plus lambda by 1 factorial, lambda square by 2 factorial, and so on, which becomes e power minus lambda. So you have e of x into x minus 1 is equal to e power minus lambda, lambda square e power plus lambda, which is equal to lambda square. Therefore, e of x square, which is defined as e of x into x minus 1 plus ex. That becomes lambda square plus lambda. This is the second raw moment, which is our mu2 dash minus mu1 dash. So now we have e of x square, so we can obtain the variance. Variance as e of x square minus ex whole square. So e of x square is lambda square plus lambda minus ex. In the previous step, we computed ex. Ex is observed to be lambda. So we have lambda square minus lambda square, which gets cancelled. So we have variance of x is equal to lambda. So we have poisson distribution, a special distribution where mean and variance are same. So you can imagine if our mean is large, variance is also large. So that means what? For larger values of lambda, much variations will be observed. So when we say lambda high, that indicates, very much fluctuation in the values of x. Naturally, that has to happen because we say x takes value 0, 1 to infinity. And if you are observing a very large value for lambda, you will observe very large values. I mean, the number of cases where x has non-zero probability will be very high. So we have seen this also in the last class. By computing the probabilities for various values of lambda, I showed you how probabilities concentrate with x equals 0, 1, 2 only when you have lambda goes to 0. As your lambda becomes larger and larger, you will observe probabilities for much of the values of x. So that is what it means. So if they ask for 1 mark, name a distribution where mean is equal to variance, then one such distribution is Poisson distribution. So there are other distributions also where mean is equal to variance. We'll look into those cases as well. Now, if you look into the relation between mean and variance of binomial, so that I forgot to tell you, relation between mean and variance of binomial. Sorry, mean and variance of binomial. Binomial distribution of the jaga idra and haki illa bracket binomial binomial. So they have the same features. So we have mean as np and variance as npq, where q is less than 1. So naturally you will observe npq less than np, which implies mean is always greater than variance or variance is always less than mean. So this happens always with respect to binomial and Bernoulli distribution. So if they give you the values of mean and variance, and if they say, can this be taken as mean and variance of binomial? Observe the values, see whether mean is larger than variance. Only then you can consider them as mean and variance of binomial. For example, say if you are observing, say mean is equal to 20 and variance is equal to 10. And the question says, can this be taken as mean and variance of binomial? You see, mean is larger than variance, can say yes. So there exists some n and p such that this will be always satisfied, so that you can say it is the mean and variance of binomial. On the other hand, if you have a case where say mean is equal to 20, variance equals 25, and now the question says, can this be taken as mean and variance of binomial? and we have a condition. Mean is always greater than variance, but here 20 is not greater than 25. So you cannot find n and p satisfying these two simultaneously. So I'll observe either your p goes, outside the limit 0 to 1, or n might become negative, so which doesn't satisfy the condition that n is integer and p becomes 0 to 0, p lies within 0 and 1, such that it is satisfied. So we say this cannot be taken as mean and variance of binomial. And the same for Bernoulli. So even in Bernoulli, we have PQ, and if you observe, PQ is always less than P because you are multiplying P with an integer, with a number which is less than 1. So PQ is obviously less than P. Therefore, we say mean is always greater than variance. So we have mean equals NP, variance of Bernoulli equals NPQ. And we have q less than 1 because 0 less than q less than 1. So naturally, we have NPQ less than NP. So just multiplying, NP on both the sides of this inequality, we get NPQ less than NP, which indicates variance less than mean or mean greater than variance. Okay, so we're done with the mean and variance of binomial, and will not, invest time in deriving mu3 dash, mu4 dash, because for that we need the factorial moments. But it is very easy in case of poisson because you'll just have to do the expansion of your x factorial in the denominator. For the next case, mu3 dash, you will consider a of x into x minus 1 into x minus 2. You can easily cancel out. You will have, lambda power x by this. So your lambda starts from actually x is equal, the expansion starts from x is equal to 3. So I'll have lambda cube. So I'll be taking that lambda cube outside. So e of x into x minus 1 into x minus 2 actually produces lambda cube. By using this, you can obtain e of x cube, which is our new theorem. So you can refer the binomial section and obtaining these, cases where you have factorials. And similarly, you derive it a case for r factorial moment. And then from that, try to obtain beta 1 and beta 2. So that is given as an assignment. Now, the method what I use is the method from the MGF. MGF is defined as expected value of e power tx, which is for a case of discrete, it is e power tx into